Welcome to Chibuzor Mathphysics. In today's video, we are going to be dealing with diagonalization. So in today's video, we are going to be dealing with diagonalization. What exactly is diagonalization? Mainly when we talk about problems in diagonalization, it will be more concerned in finding the basis for Rn that consists of eigenvectors of an n by n matrix A. So we are going to be more interested in this n by n matrix A, but this n by n, of course, in the previous videos I told you that n by n matrix is nothing but a square matrix that have equal number of rows and equal number of columns. So such bases can be used to study geometric properties of A and to a kind of simplify various numerical computations. So these bases are actually of physical significance in a wider variety of applications, and I will mention one or two before the end of this video. So our first objective in this video is to show that the following two seemingly different problems are equivalent. One, given that we have an n by n matrix A, there exists an invertible matrix. So there must be an invertible matrix. There must be an invertible matrix. Invertible matrix P such that the P inverse of matrix A, AP, is diagonal. So this is our first target. And this will become our problem 1. So let's put that well. So it is given an n by n matrix. We have n by n here. Given an n by n matrix. N by n matrix. And that matrix is matrix A. There exists an invertible matrix P such that P inverse of A, P, is diagonal. So the next problem, number 2, will be that given an n by n, let's have that down, given an n by n matrix A, does A, which is matrix A, have n linearly independent? Eigenvectors. Independent eigenvectors. This is eigenvectors. This is why I like linear algebra, because this is actually going to my field. We are entering to pure mathematics, where we need to prove that some functions or some formulas that we use is actually true or false. So we are talking about diagonalization, and in diagonalization there are two things that we tend to investigate. That given this n by n matrix, and we know what it is, that n by n matrix is simply a square matrix that have the same number of rows and the same number of columns. So this matrix P, such that P inverse of AP is diagonal. And the next problem we intend to investigate is that given an n by n matrix A, does A have n linearly independent eigenvectors? If these two conditions are satisfied, then it means that our matrix will be diagonalized. So let's see how this can be brought into more physical, in more physical way, that it will make sense for an ordinary layman who is listening to this, because mathematics sometimes is a bit odd for us to define it. But that's exactly what we are trying to say. So the matrix product is P inverse A, P inverse AP, P inverse AP, and this appears in the first problem. What we are saying here is that there is a similarity transformation. There is a similarity transformation. So such products are very important in the study of eigenvectors and eigenvalues. So we will begin this video with this terminology about them, and we will be using what we call similarity. So if A, let's say that if A and B are square matrices with n by n, B is similar to A. So what we are saying is that if they are of the order n by n, then it therefore means that B is similar to A. Similarity we write like this in mathematics. So B is similar to A. So this B is similar to A, such that B will be equals to the P inverse of AP. So stay tuned and enjoy this video as we prove that the above statement is true. Enjoy. I remain your friend, Galagash. So let us start by proving that proving the theorem. The theorem in this diagonalization, and the theorem is saying that if we can let A, B, and C to be n by n matrix, to be n by n matrix. What we are simply saying is that this matrix is a square matrix. We start with number one. Number one, we are trying to prove that A is similar to B. This means similar. So we are proving that A is similar to B. So for A to be similar to B, let us prove this. A is similar to B. It means that this implies that there exists. This sign means it implies that there exists an invertibility. There exists an invertible matrix. Invertible matrix, and that invertible matrix is matrix P. Matrix P, such that P inverse, like we said initially, of AP is equal to A. Let us take P. Let us take P to be equals to some identity matrix, like you observed initially when we are looking for eigenvalues and eigenvectors. We usually look for some identity. That's why we had A minus lambda I. where I is an identity. So take P to be equal to some identity. If we do that, this will imply that I inverse, because we are replacing this I to be P. So I inverse instead of P inverse of A become I. And this will simply mean that I inverse of A is equals to IA. And what is IA? We know that when you multiply identity with A, you will simply get A. So this will be A. So therefore, it means that A is similar to A. And this is how you prove that the statement is true. It looks odd, but when we go to computation, you understand why this is similarity and why this is true. This is the first one, and we've proven that A is similar to A, because we started by saying that if A is similar to A, it implies that there exists an invertibility matrix P such that P inverse of AP is equals to A. Then we take the P to be an identity matrix when we refer to the previous video when we talked about identity. So P here represents an identity. So it means that instead of P inverse like we have here, it becomes I inverse of AI, which is equals to I inverse of A. And that will simply give us I or A. That will be IA. This is A, and we know what it means. IA simply means A. So that if you multiply these two things, it means that A is simply similar to A. Okay, let us see if A is similar to B. So in the case of A is similar to B, let's say that there exists P such that we have our P inverse as usual of A, P. Now it is equals to B, because we are saying that A is similar to B. So what this means is that P inverse of AP is equals to B. Let's set Q, for instance, to be equals to P inverse, because in the first one we set I to be that. So it means that we'll have Q inverse of BQ to be equals to P inverse of another inverse. So, and this is P of P inverse, which will give us P BP inverse. We are trying to prove that. This will mean that you need to note that P inverse of A, P inverse of AP, which is equals to P, can be written as P inverse of A. Then we have A, that is AP, and this will simply be PB when we open up that. So this means that AP will simply be PB. Therefore, AP P inverse is equals to PB P inverse. Therefore, we can say that A is equals to PBP inverse, which means that A is similar to B. Anyway, this is pure mathematics, and you simply need to go through it one more time and you get the concept. But when we dive into computation, you will understand this proving. What I want you to note here, if you can't get anything, at least get that A is similar to B and B is similar to A. See you in our next video. I remain your friend, Galagash.